Hey, I was gonna move on to my next section of teaching content about resistors, but then I realized I wanted to do one more example because I haven't actually given a circuit where I solve for a resistance. I've always been solving for voltages and currents and powers, so I want to do one quick example where I actually identify an unknown resistance in a circuit. So let me go ahead and draw that up. Okay, here we go. This is the example circuit I want to talk about today. And what I've drawn here, I know this looks kind of weird. I haven't necessarily drawn a circuit with these kinds of angles or connected in this way. And you just have to realize that, look, okay, this is mainly a contrived thing. I mean, it's not often you see schematics where people give diagonal elements and wires that look like they're connecting in suspicious ways, or it's not obvious what's going on. And yeah, a lot of times stuff like this is just to fool you in an academic setting. If you were practicing at your job as an engineer, you'd get dirty looks from anybody if you tried to show them a schematic that was deliberately confusing like this, because that's totally not the point. If anything, schematic drawing is one of the most difficult things about being an engineer, because you're trying so hard for your ideas to be communicated clearly. But in any case, I actually like this example because I'm going to introduce a skill or a technique that you can use to make your life easier when it comes to analyzing circuits that we haven't done yet. So let me start by talking about what I've drawn here. I have an ideal voltage source. This is a 12-volt source. And then there's four resistors, a 4 ohm, an 8 ohm, a 2 ohm, an unknown resistance here, Rx, and then we're given that there are 2 amps entering this 2 ohm resistor with this polarity, this reference direction. So then the question, like I alluded to before, is going to be, what is Rx? So we're going to calculate, we're going to identify this unknown resistance in our circuit. And if you're anything like me, like I just talked about, if you're a new student in electrical engineering or EE 101, you're going to see this. You might be confused, you might freak out, you don't know necessarily what's going on here. Is this a short? What's this doing to my resistances and to my currents? What is going on here? So it's really not that complicated, but it's kind of masked by the way this is drawn. So this is a great opportunity to redraw our circuit, and this is something that I haven't done yet, but we're going to do now. And you're going to want to do this at times when you're given kind of hocus pocus problems like this in school. You want to redraw things just to make it easier to look at, make it clear what's going on, and usually what that does is make it more obvious where currents are flowing and exactly what elements share voltages and whatnot. So the first thing to remember when you redraw circuits, of course you have to redraw it as an equivalent circuit. So I'm just redrawing it. It's still going to be the exact same circuit in functionality, in the elements, and the way they're connected, everything. It's literally just essentially what you can do is reorganize ideal conductors as long as you don't break any nodes or attach to new ones. And the main thing is this line across the middle and the fact that these resistors are angled off like this. I really don't like this. I think this is super unclear and just deliberately pesky. So give me a second to redraw this, and then I'll start doing some analysis. Okay, here we go. And let me just indicate here a redraw. So I've redrawn the circuit here, and this is an identical circuit. It's exactly the same. I'm just trying to make it a little bit more clear of what's going on here by the way I've connected the nodes with my lines, with my ideal conductors. So I'm really just emphasizing the fact that this 4 ohm and this 8 ohm are in parallel, and Rx and this 2 ohm are in parallel. And so these two, where all 4 resistors connect, these 2 nodes on this side of the 4 ohm and the 8 ohm connect together, and then this side of the Rx and the 2 ohm connect together, and then all 4 connect together. So really there's 4 elements touching this node, but drawing it this way is really helpful but because it kind of helps you envision that really what you have is two parallel combinations in series. So you have this parallel combination of the 4 ohm and the 8 ohm, and this parallel combination of the RX and the 2 ohm, and they're in series. So this parallel combination is in series with this parallel combination. And really that just helps you visualize where the voltages are, what voltages are equal, and that the total current coming from this source, flows through all these elements. And I just think this is a lot easier to look at than this. So let's start. We want Rx, and we really have to work with just whatever we have. So I think the obvious starting point is the fact that we have this 2 amps entering the 2 ohm resistor here. So, okay, Ohm's law, great. We automatically know this voltage. V equals IR. So we have 2 times 2, we have, I'm going to label this Vx right here. So Vx equals 4 volts. And that's because, like I said, these two resistors are in parallel, so they share the same voltage. Vx is across the 2 ohm and Rx. So this current through the 2 ohms gives us Vx, and it's 4 volts. Okay, that's fantastic. But the next thing is, okay, we have Vx, but in order to calculate Rx, we actually also need to know its current. We need Ix, because by Ohm's law, Vx divided by Ix, that volt-amp ratio, will tell us Rx. That's the definition of Rx, is the ratio of Vx to Ix. So naturally, we want Ix, and so naturally, we'll probably want to apply a KCL at one or more of these nodes. The problem being at this node, for example, we only have one of the currents when there should be 4, because there's 4 elements touching this node here. So we don't know the current through the 4 ohm and the 8 ohm. Well, how can we get those? Given that we know their resistances, if we knew their voltages, then we would have their currents. Luckily, we also have in our employ the tool KVL. So, given that we have these different subsections of the circuit in series, we can actually travel around this loop and solve for this voltage using KVL. So I'm going to say there's a voltage across these 2 resistors, Vy, and remember, they must share the same voltage because they're in parallel. So really, there's 3 elements in this circuit, if you will, and they're all in series. There's a source in series with this parallel combination, which is then in series with this parallel combination. So there's really only 3 voltages here. There's the source, Vy, and Vx. And that's a really good way to look at things when you're talking about series versus parallel, is look at like, okay, how many voltages do you have in this loop, or how many currents do you have in this node? And so in this case, we can easily write a KVL where we step up this 12 volts, and these are all resistors, so we know they're stepping down. We're going to step down Vy and Vx, and for KVL to work out, we know that the step ups have to equal these steps down in potential. So it's simple to write that 12 volts equals Vy plus Vx, and given that we already know Vx, therefore Vy equals 8 volts. And that's fantastic because now we have a voltage across 2 resistances, which means we actually have 2 currents as well. So just doing this math quickly, V over R will give us the current. So 8 divided by 4 is going to give us 2 amps in this element, and 8 divided by 8 is going to give us 1 amp in this element. And now the KCL should be pretty easy as well, because we know the current entering these resistors also leaves these resistors and therefore enters this node. So we have 2 amps entering the node here, 1 amp entering the node here, and then we have 2 currents leaving. So the sum of the currents entering here is going to equal the total current leaving here. But it should be obvious. If you look at the top and the bottom sections here as 2 halves of an equation, you have 2 plus 1 coming in and 2 plus something coming out. Well, obviously, this other something is 1, because you have 2 coming in, 2 coming out, and that balances. And then you have 1 coming in. Well, that 1 has to go somewhere, so it has to come out. And that's Ix. So we can write Ix equals 1 amp. And that's amazing, because then, therefore, by Ohm's law, I guess I'll start over here, Rx equals this volt-amp ratio of Vx over Ix, which is 4 volts divided by 1 amp. 1 amp. Therefore, Rx equals 4 ohms. And that is the solution to this problem. So this is kind of a nifty problem. We did a resistance calculation, we did a circuit redraw, and we talked a little bit more about the intuition behind KVL and KCL. So really, you know, once you master these tools, KVL, KCL, seeing a circuit for what it is, seeing parallel and series combinations, being able to look at this problem without doing this redraw, you can do this stuff really fast. So this doesn't take a 15-minute video, or however long this is going to turn out to be. You know, once you'll know that you've mastered this when you can solve this problem in 1 minute, you know, 30 seconds to 2 minutes, you know, somewhere in that range, and you know you've got this down. Because you don't have to say all this stuff out loud like I am. You don't have to do all these labels, although it is still good to do this. It's good practice, even for me. But you know, you don't have to write all this out and do every single little step. Like it becomes really quick once you know what's going on. And so again, I would say a problem like this, once you're really getting a grasp of this, just several minutes at most, and then you should be able to arrive at this. And then, like always, you can walk through the power calculations if you want. I trust you to do that at this point. And again, just do your best to check your work or catch any mistakes that you can. So I hope this was helpful. Let me know if there's any way I can improve this in format or style. Anything in particular you'd like to see, specific circuits or specific questions that you have, let me know, because I'm definitely interested in helping in any way I can. And I'm thinking the next thing I'm going to do is I'm finally going to start talking about equivalent resistances, or formulas for equivalent resistance. Or rather, you know, what happens when you start stacking resistors in parallel, or stacking resistors in series, and how can we reduce circuits and make them more simple to look at. As it turns out, there's actually an alternate way to look at this circuit. So everything that I have here in this box, you could look at as one giant equivalent resistance. And so I'll talk about that in the next video, so I'll look forward to that. Otherwise, I hope you have a great day.